Okay. So I have a model that I made myself. That's just a simple kind of city model. This is the one you guys remember from a few weeks ago. And what I'm going to do with this is a couple different forms of analysis. The first form I'm going to do is what's called like an isovist, and it's a method of analysis that it's essentially you have a point in space, and you're going to draw lines rating out from that point, and whenever they hit something, you're going to stop drawing a line, right? And when you have all those lines, that's going to create a polygon that just shows you what a person can see from that point, okay? And there's a whole field of study that engages in this called space syntax. You guys might have heard of it. It's something they do at Michigan. They do it like at Georgia Tech. And it's basically a way of understanding how people use space. So if you're going to do an analysis of your site, of what people can see on a site, which is something I think a lot of you guys have done before, you can do it computationally using this method. So if you go into Grasshopper, there actually is an isovist component. If you go under intersect, and actually just click on isovist, okay? So compute an isovist sampling. So let's just start by looking at isovist and what isovist wants, okay? Isovist is going to take a sampling plane and origin, which is pretty self-explanatory. It's actually going to be the point from which you're going to take the isovist, and then a sample count, which is the number of lines it's going to generate out from itself. And the more lines you have, the longer it's going to take to do the intersections, but the more fine your kind of view polygon is going to be. And then a radius, which is how far out those lines are going to extend. And again, the further out you go, the more buildings you might catch, the more it might calculate. And then lastly, obstacle outlines. Okay, and those are the things that you're going to intersect with. Okay, so that's actually well. First things first. We can use a point to define our sampling plane and origin. So I can put a point. Actually, I've already got a point, but I'll delete it for now. Let's make that point. And set it. Okay, so that's in the system. And then do a slider for number of lines. If for a single point, you can do quite a few. Set this to be between 0 and 250. Don't need decimals though. Okay, so we got that. Radius, let's go ahead and do that as well. I'm not sure what my units are, but it's fine. And then lastly, the outlines. And if you had a two-dimensional map of something, it'd be really easy just to take all of the figures on your map and you'd be done. But we have some 3D geometry right now. So what we need to do is we need to convert these buildings to their outlines on that sort of plane. Okay, and fortunately, there's a really easy way to do that. You look at the intersection. We didn't really do a lot of this, but there's you can find all kinds of intersections in Grasshopper, and there's all different types of them. And there's actually too many. I mean, anything you can think of. A line in a line, a curve in a line, a boundary representation in a line, a mesh in a line, and then there's the other ones like a curve with a curve, B-rep with a B-rep. So these are all. You'd find the specific one that you want. The one in this case that we're looking at, I'm going to say is probably a B-rep with a B-rep, or a B-rep with a plane. These are all boundary representations, and in fact they're just like boxes, so they're the perfect boundary representations. So we're looking at the intersection of that box, which in this case is the building, right? That geometry with some other thing, and that's going to give me a line. That's going to give me an outline. Okay. So it's kind of like a section, in fact, yeah, no, it's not going to say that. Okay, when you actually get it, it says I think B-rep and B-rep. That's what we want. I lost it here. B-rep with a B-rep. Let's see, first B-rep, second B-rep. Okay, so what we actually have is a collection of things. So we're going to use a geometry component to hold all these. So you're going to click all these. And you can have multiple things. You can actually say set multiple geometries, or set multiple lines, or set multiple curves. We've done a lot of things where we set one. You can put multiple things into those baskets. So set multiple geometries. You can see that they turn green. Okay, so that's one set. And then let's look at this other one as a piece of geometry, and we can set one. Okay, and then if I go ahead and hide all this stuff, and if I go ahead and turn off my geometry, you can see that it gives me the lines on that. So where those things intersect, it's going to create a curve for me, and those are the boundary lines I'm going to be using for the isovist. Okay, you can do this with anything. Again, you know, this kind of technique, it's parametric. So if I had something that was changing on that surface, or I changed that surface, I would still get that boundary line. Okay. So I have a list of curves, and I'm going to I can plug that in for this. And you can see what this actually gives me is not like what I showed you guys. What it gives me is a list of intersection points. Okay. In fact, it's actually giving me 12,000. Wow, it's giving me a ton of them. So I might need to adjust that. But let's go ahead and flatten these out, actually, see if that helps. Now, 177 is a little bit more manageable. Okay, this is for data structures. Like when you look at something, I was talking about this with like the graduate lab. You always want to check and see what you've got, because that can tell you whether you need to flatten a structure or not. I don't think I need 1,200 like data points for this thing. Like that's actually going to incredibly slow it down. What it's doing is it's doing the same 177 like for each one, because I set this to be 177, and I have these boundary lines in these sort of groups, which gives me a lot. But if I flatten those so that they're not in that structure anymore, then I only have 177 samples, which is manageable. You're going to see that's probably fine. But what I end up with is a list of points. Okay. And so what I need to do is I actually need to draw the isovist now, okay? And this is actually pretty simple. What I'm going to do is just take a line component, and part of the line is going to be, so line takes a start point and an end point, and the start point of the isovist is going to be my original point, and the end point is going to be these points, and that's actually what gives you the isovist. And you can see, though, that those x's are the points where, so what it does is, think about it, it does 177 things in a big arc, and some of them intersect things and some of them don't. And the ones that don't are the ones that are going out. So there's a radius, okay? And that's the piece that you can control parametrically as well. So that's the radius. Okay, and you can see if I don't go far enough, like I don't get this other building. And then this is my, I can change the number of lines I have. Okay, and so you could do like you could bake those lines. You don't need to make 2D because they're lines, right? And you can make that a diagram for yourself. Okay, and you could do several of these. And this piece is actually, parametric. In that if I move this point around, it's actually going to give me different readings of things. Okay. And I'm not going to do it because it's going to take a little bit of time, but if you know your data structures, you could draw a line of a person walking through the city, and then you could distribute points along that line, and you could draw isovists from each point on that line, and you would get what a person would see as they walk. Okay. You just got to manage that, because then it's going to get a little bit complicated. So there's going to be some grafting involved with that. Okay. But that's the general idea. Or if you didn't want to do it computationally, you could just do a couple of different ones of these and then kind of layer them in Photoshop or something like that. That would work, but it wouldn't be as computational. Okay. So again, this is a lot of you guys do these kind of like vision studies where you're talking about like what you can see from a certain point. This is like a better kind of mathematical way of actually like determining that. Okay, and it's really quick. It'll work with anything that you can throw at it, basically. Okay. Any questions on isovists? Okay. So I'm gonna look at another kind of analysis here. Real quick, yeah, actually, yeah, I'm gonna look at a different form of analysis. So, another thing that you might measure if you're doing, this really applies to like an urban study or something like that. But let's say you had like this enormous like GIS map, and you had all the elevations for all these buildings. You had this really big city, and you wanted to look at you wanted to graphically see the heights of the buildings, right? You wanted to see where, or you wanted to see where, like you're looking for an area that's kind of like low density. So you want to visualize areas where the buildings are very short. So to make a map like that, the first thing you need to do is figure out what the height of all these things are. Okay, all these different structures. So what you can do, and this is a really good lesson actually, in just thinking about all the data that we can get from an object. So again, we're going to set all that geometry and put it inside a container. Okay, so now it's all there. Okay, now there isn't anything that you can just plug in that says, okay, give me the height of this thing. Okay, because what's height really? In this case, it's really easy because all these kind of share the same kind of base. So let's just go ahead and use that as a thing. So what we can do is we can look at those geometries, and we can get the highest z coordinate of each of those, and that's the height. Okay, because they all share the same height. Otherwise, what we could do is we could get the lowest z coordinate and the highest z coordinate of each of these if they were on different planes, and you could subtract one from the other, and that would give you the height of it as well. Okay, so you got to think of these as like data. A really easy way. These are all. I missed one. These are all like boxes, so it would be very easy to actually figure that out because they're just kind of flat. If you had something that was crazy or like warped or had an odd shape, that might be hard to do. But there's actually a pretty easy way to find the volume of anything, and that's to do a bounding box. And we saw one of these when we did that morph thing, where we did the two different kinds of things that we morphed around that sort of tower. A bounding box just creates a kind of an envelope around some object. And if we measure the bounding box, that geometry, we can find that data really, really easily. Okay? Instead of having to actually look at all the points in the object and like try to figure things out like that, if you put a bounding box around something, and actually just let me really quick just kind of graphically demonstrate what that is. So if I had like a torus, which is a donut, wow, it's donut day. All right. So I have a torus, which is a donut. It might be hard for me to find out like how tall that actually is or what that is. But if I plug that in, I can get the bounding box of that torus. And then if I look at the top corner of that, I know how tall the torus is. Okay. If I had a cone, if I had some kind of whoopy thing, if I put that inside a bounding box, I just measure the bounding box. It's an easy way to get the data out. Okay. Okay. So, let me get rid of my donut here. Okay. And so that's the principle of what I'm going to do here. And again, it's really easy with boxes, but okay. So back into the geometry container they go. We're going to hide those. So we get the bounding box. Okay. And now I've got, they're basically the same thing, but if I had different shapes, I would use bounding box. Okay, and then I could go into each of those things, and I could do like a list where I could figure out in each of these which vertex of the box the top corner is. So if it's like vertex 6 or vertex 4 or something like that, I could do that. Another way, there's actually a component that's called box corners that actually just gives me, it's kind of insane, but you put this in and it actually gives you, it gives you access to all those instantly. So corner, because think of it, it will have 8 corners. It's got 4 on the top and 4 on the bottom. So that's A, B, C, D, E, F, G, H. Okay, I can just pull that point out from there. So it's a little bit easier. Okay, And it's actually nice because these aren't in, they're not in sort of like a grafted form. So out of the bounding box, I can go in, and I'm just gonna, I think it's probably, if I look at the Z coordinates, I think we're safe with any of these last ones, so like H or something like that. So I can go in, and I can extract data from any point. So we've seen stuff where we take a point and we put data in, and where we take data and it gives us a point. With the point decompose, I can take a point and I can pull out the XYZ data from any point. Okay, that's a quick way of getting the information out. So I'll take my H point, and that's actually going to give me a series of Z's for all of those points. Okay, those are the heights of each of those things. Okay, so what I'm going to do with that is I'm going to find a way to visualize what that is using color. And the way to do that is there's a gradient component. And what a gradient component does is that you give it some kind of a range from some number to some number, and it will return a color based on that number. Okay, and the color is whatever this gradient is. Right now it's pink. You can change it to all kinds of things. So if I right-click this, I can go into my presets. I can do it as a heat map. I can do it as a black and white gradient. I could do it as a rainbow. I can do it as a kind of hot and cold, and then you can also make any gradients you want. But I'm just going to do it as kind of a heat map for right now. Okay. So again, this is your lower limit, and then the other one is your upper limit. And then that's gonna and then you can plug in like a certain kind of like parameter, and that'll actually spit that out. So what we need to do is we need to find the upper limit and the lower limit of the data we have, and then when we plug these in that building order, that's going to give us the color we want to make each building. Okay. So we have all these. What we want to do is find the upper limit and the lower limit. And to do that, I can just put in a bounds object, and that's going to give me like a domain from 7 to 22. So that's what I started out with. I have all these numbers. A bounds object will give me the upper and lower bounds. The upper and lower bounds are what I want for my gradient. Okay. I need to get them out though, because I've got one thing here and I need two here. I need the upper and lower separate. So I can actually get the domain components. This is a domain. Get the domain components. So now I got the start of the domain and the end of the domain. Okay, so I plug these in. Start is this one, end is this one. Okay. Then if I plugged in my list again into here, well, it's going to give me colors. Now I need to do something with those colors. Like I actually have a problem. How do I get the colors back onto the original objects? Okay. Colors only apply to like meshes. We haven't really talked about this too much, but in Rhinoceros, if you guys have used it a lot, pretty much everything starts off as like a surface or some kind of thing that's actually like a poly surface. They're these kind of complex curves. Meshes are kind of dumb, are these dumb kind of like polygons, and in order to make anything have like a color, you need to actually convert the surfaces into these dumb kind of polygons. So we need to actually go back and convert our geometry, which is a surface, into a mesh. And so there's all these meshing tools, and anytime you see something that has this kind of faceted kind of characteristic, you're probably dealing with a mesh. Okay. A lot of these like triangulation tools, these are things I'm going to talk about later today, have to do with meshes. So you just have to basically convert something into a mesh. And like fortunately, there are lots of ways to do that in here. The easiest way to do it is just to do a mesh BREP. And what that does is you can take a BREP and it'll attempt to make it into a mesh. Pretty simple. So I take my geometry and I get a mesh. Okay. It really works well for boxes, right? Because they're just really simple geometry. If you have something that has a lot of curves or a lot of things like that, it might not translate too well. But for like buildings, for the kind of things we're doing right now, it's absolutely perfect. So I take my mesh, and then there's a thing called mesh color. And so what we could do is we have a mesh, plug it in. Then you can add the colors to it. So the colors come from here. And I actually need to graph these, I think. Yeah. So this is where your data structures come into. Okay. What you need to do is make sure that that applies to the right geometry. I need to turn some things off here. I've got all kinds of stuff turned on. Okay. Okay, and so the tallest one is the red one. Okay. So to take us all the way out here again, start with my geometry, which are the three-dimensional things in my piece. And the goal is to find out what the heights of those things are, and then to basically map that data onto this color range, and then paint it back onto those pieces. Okay. And the way I do that is I got two separate things going on. On one hand, I'm trying to get that z-coordinate for each one, that top z-coordinate, and I use the bounding box. And I sort that using the bounds. Like I find out what the maximum and what the minimum are, and then I can use the gradient tool to take that data, and that's going to give me color. That's organized by height. And then I need to paint it onto a mesh. I need to make a mesh from the geometry, and then I use mesh color. Okay. And then this is a quick way to do diagram. And again, you can go in and change the gradient to all kinds of different things. And you know, I could mess with that range. Hot and cold. Well, this one's kind of backwards here, but the tall one's the coolest one. So there's lots of ways to do this, and you can do this with any information that you have. You could do it with the distance from one thing to another. You could do it with the volume of something. You could do it with the area of something. Anytime you can get numbers out of some geometry, you can use that kind of gradient thing, and you can essentially create a diagram really, really quickly. And then again, this would work for very large scale things. This would work in a lot of different contexts. So this is the general idea. If you can extract data from some kind of relationship, you can essentially graph it here. Okay? The tough part is just you have to actually know that you got to get meshes to use it. Otherwise, this doesn't really do anything. Okay, so it's a really basic thing. I could go in and actually just do this. Take the volume. So I can take the volume of the bounding boxes. So just find out how much kind of total square footage, let's say, something has, right? I mean, this is kind of a cheap way to do it, but I could do that instead. Take the volume, find the bounds for it. What am I missing here? Does it give me any volume? Yeah, it should give me volume. Oh, yeah, I said I got to plug this back in for T. Okay, so now, again, the blue is kind of high, red is low. Let's go back to the heat map thing, actually. So you can see that this one has the most volume. The narrow towers, I don't have a lot of volume. The yellow ones have middle volume. Okay. So again, take some information about your object. Again, I'm using bounding box to find the volume. I could actually just get the volume of the object. Actually, it wouldn't matter how crazy it was. Volume could find it. And then that data, I split the bounds. Put it into the gradient. Put it back into the mesh. So there's lots of different ways. You could diagram the same city in lots of different ways. Okay. I showed you a demo before of a point, basically, of finding the proximity of something. Let's go ahead and delete this. So this is kind of like the attractor code that we had. So what I can do is I want to find the distance between all these points and some other point, right? So for instance, like the place where you want to build your building or some other structure, and you sort of want to measure graphically how far or how near things are from that point. So you can go in, find the distance between the centroids and my point, which is going to be this one now. Get a list of information, plug it in, plug it back in. Once you have the pattern, it's actually very easy. So again, the distance now, green stuff is closer, red stuff is further away. So now those are further away, okay? Just once you have the principle of it, once you have the structure, it's really simple, okay? Again, it works great for your square building, so it needs a little bit of tweaking for more complicated things, but the idea is generally there. Okay, so any questions about this kind of diagramming, you guys? To get it out, I will post a component. You can't render this. At least not right now. Maybe in a future version of Rhinoceros. Well, you can't render anything until you bake it. But if you bake this, you don't get the color right now. There's a component that I would give you that's that basically transfers the mesh stuff to a texture and then automatically applies it. And you can't get it out without that component. There's no way to do that. So if you did try to do this, you would get stuck at that point. So I'll post that on Moodle. If you need it, let me know. Okay. So if you want to render this stuff, you have to use that component. It's just a little plugin for Rhinoceros. Because it just doesn't work that way with meshes. Okay. So we've covered distance analysis, the isovist, height analysis. Okay. The next one I want to talk about is meshes, different kinds of mesh patterns. Okay. All right. So what I'm going to do is I'm going to make a really big surface. Okay. So there's different kinds of tiling, different kinds of meshes. You'll see this a lot in these kind of fancy computational, maybe like magazines or books. You get this sort of leaf type pattern, like a Voronoi diagram. Once I show you what it looks like, you'll recognize it right away. Basically, what it is just an algorithm for finding the midpoints between points on a surface, and it creates this kind of crackling, faceted, kind of alien-looking thing. It's really easy. Okay, all these computational guys have this stuff, and it's actually really sort of trivial. The other thing is anytime you see something that's just kind of just something that's kind of faceted, this is a way to apply that kind of triangulation. So if you just have a bunch of points and you just want to connect all the points to their nearest neighbors to just kind of create a mesh or kind of a frame, you can use this kind of tiling. And then lastly, there's this quad tree, which is actually a form of visualization. What it does is it counts the number of points in a cell, and then it can subdivide a cell based on that. And again, that might be something that you might be able to use in one of your projects. I'm going to show you all three types just so you understand the idea of it. But again, these are just basically about points on a surface and the different ways that you can use them to subdivide that surface. Okay? We've seen a lot of ways to divide a surface. It's just really sort of like regular, where we just say okay, the number of U's and the number of V's in a row. This becomes a bit irregular. Okay? And so if you can find a way to generate those points, even if it's randomly, these will give you interesting patterns on your surface. Okay, so maybe there's a logical way that you make the points, and then these help you subdivide. It all makes a lot more sense when I actually show you. Okay, so the first thing I want to do is I just actually want to make, well, we'll start with the old standby here. This will work. So I'm going to do my surface. I'm going to divide it. And then I'm going to do an ISO trim. And the reason I want to do this way for now, I could make a bunch of random points and then draw a box around them. But in this case, it's I probably have something on my building that's a certain shape, and I want the points to be on that shape. And so by starting with surfaces that are subdivided from the surface, I can guarantee initially that those points are on the surface. So if I go in and say set surface, okay, got all these, right? Look familiar. And then I'm going to do, I can do an area to get the center points. Okay, Then I could do things like I can move them somewhat randomly. This is kind of getting into some of the stuff we did in processing, right? Where if you take a point in space and you give it like a little bit of wiggle, like two this way or two that way, or that's how you get a little bit of randomness in your points. They start off all on the grid, but you're going to disturb the grid a little bit. Okay. Yeah.
Can we use decomposer, like to get the point?
Yes. Yeah. You could use it. You could just decompose. Again, you could just make the points randomly. You can just take a XYZ point and then just pipe random numbers into it, and you get just random points. Yeah. There's lots of different methods for this. This is kind of one. This is like our processing method. So again, if I take those points and I'm going to move them I'm going to move them in the X first, and I'm going to move them by some. Okay, pull this out here. So I find the wrong thing. List length. So this is a pattern that we use a lot. So I find the list length of the number of points I have, plug it in for the number of random values, okay? And then that's going to give me, let me hide all these. So it's really subtle right now. I'm going to go ahead and increase the range. So I could say between, I don't know, -3 to 3. It's a pretty, yeah, okay. So that's a random X. And I can go in and take that same geometry and do a random Y. You got to keep turning preview off here. Okay, so now we've got a little bit more disturbed points for these. All right. Actually, let me just, for the heck of it, put in a random seed as well. Okay, so plug this in for S. So you can see that you're going to get different things. Okay, so we have a bunch of points and we have some kind of boundary, kind of edge. Okay, so and what you'd want to do is ensure that they don't go outside of it. You'd want to set that range so that they don't violate that edge. And you could do that mathematically, or you could just eyeball it. That's fine. Okay, once we've got that, now we can start doing some triangulation here. So with the edges, what I can do is I can take these, and if I plug that in, it's going to give me the triangulation for that entire. So it's going to connect all those by some line. So again, like the Delaunay triangulation, which is just one of many, many kinds of triangulation, is going to look for its nearest neighbors, and it's going to try to connect all those by the same lines. Okay, so if you give it any batch of points, even points in 3D space, it's going to try to connect them by lines. So you essentially get like a network graph. And depending on how you do it, it could get kind of weird if this is one of the edge points. But if I don't like that, I could always keep playing with the points until I get something I like. And actually, let's go ahead and do this. Let's make this a little bit more interesting yet. Let's add these in the Z as well, because that's actually where this can kind of get interesting. Okay, so I'll hide this. Disconnect. Okay, and Z. And I'm actually going to increase the range here to 6. So if I look at that, so it's going to give me a bunch of points. And if I connect that again, let me go ahead and hide all this stuff too. Okay. So it begins to give me this kind of frame. Now, if you notice, I hope you notice, these are just the edges. These aren't actually any geometry. It's not a surface. Okay. To get that, once you have that, connectivity, you can do mesh. So there's Delaunay edges and Delaunay mesh. Okay. And you can do the same thing where I could plug this in and it's going to give me, so the mesh piece of it, we just talked about meshes, right? So that I can bake, I can make that, right? That's actually something I can put in my Rhino model. This gives me the edges, and so with the edges, I could do something like pipe them. Good old pipe. Except, what do we got? Yeah, okay, so except they're hideously, we need to flatten these. Curves. Oh, no, you know what? Yeah. All right, so now you've got your super futuristic magazine cover, architecture. And again, it's, you can play with the randomness of it. Of course, you would do this more logically, right? You wouldn't just spam a bunch of random points. I mean, you could take this and you could do one of those power curves that I showed you, where you could do like the graph editor, and then you could actually tessellate it, and then this is something buildable, right? Or you could derive something. I mean, you could take maybe an isovist or something, take the distance of something, and then actually mesh that. There's lots of, again, once you have some kind of logic behind it, though, this is how you start to coalesce that into some kind of a structure. Okay? This is one way to do that. Okay. Any questions so far on these? It's pretty basic. But the idea is that you get some points, and you can begin to kind of mesh that. Okay. Okay. Let's go back to Voronoi. See how far back I need to go. Okay, just kill these here. This might not be too pretty, but will work. So Voronoi takes points, takes a cell radius, and a containment box. These are all optional, actually, and a base plane. Let's go ahead and just see what we get. Yeah. So again, what this is doing is it's actually draws lines between these, takes the midpoints of those, and then actually draws a surface based on those. So it's actually a little bit different than that last one we saw, right? So instead of being every point gets connected to every point, it actually creates a cell for all those other points. Okay. Let me go ahead and actually change some of this stuff. Let's hopefully get some more interesting things. They don't look so hot when they're close together. They become more interesting when you get little pockets of things when they're closer together, or when things are further apart. You can see how it looks like a dragonfly's wing or like a leaf or something like that. This is supposedly a structural principle in nature, right? It's finding those points basically between other points in space. Just get this a bit more. So again, if I can, if I have a point that's actually kind of isolated, it's going to get its own really big island if I have these things faceted. So this is a way, again, of creating some order out of some other order that you've made, out of just these points, right? And then what you could do is you could put a box around it in Rhino, and then you could actually trim that out. You could use this to cut a surface. I could do a surface split with that, and then each of these is going to be a surface. Then I could cull some of those. I could turn some of them off and on. Okay, so this is a way, but again, this is just a collection of points that you could create, and then you could tile this in lots of different ways, And so this is Voronoi tiling, and you can see that it actually goes out to, and I could change the size of that box to whatever shape I want, or again, I could take some kind of curvy like pavilion, and I could just trim it out with that, like a cookie cutter or something. Okay. Let's hide those points, actually. That might, yeah. So, again, has this kind of spider webby kind of pattern. Pretty interesting. So if you've ever seen that, and you've ever wondered like how that works, it's Voronoi. So you could play with the radius of them. The tighter the radius, you'll actually start to lose some of these patterns as they don't join with each other anymore. The bounding box, I think, is self-explanatory. So you can use this with a surface split. Actually, do I have a? Yeah, I could just do that really quick. So if I make a surface, See if this works. Actually, it's not going to work because I have this points in the Z, I think. Oh, no. No, it will. Okay. Take my surface. Split. See if this works. Okay. Split. And my curves, they output as curves. Okay. This is probably going to crunch for a second. Ah, not bad. Okay. And I get, 100 surfaces. Okay, so if I go in and I turn off my original surface, and then I go in, hide this, and I go in and I turn off my Voronoi. Okay, so now I've got a chunk of something. I could go in and I could cull. And if you had the frame, right, you could begin to create some kind of effect. You could do like an attractor for your cull. You could do all kinds of things. Okay. Computers are wonderful. Okay, so Voronoi, like now you guys know, use it wisely. This is like one of the most overused things, but it's trivial. Okay. Okay. Lastly, I'm going to show you guys a quad tree. A quad tree, as I said again, is used in visualization. It's used to map things like population distribution and minefields, and anywhere. It's a way of quickly visualizing how much of something is in a particular grid by subdividing that grid. So just drop a quad tree in there. It wants points. It wants a plane. It wants. Oh, we can change some settings here. Okay. So if I plot my points in. Actually shows me the points. So you can see, okay, base plane, square leaves, permitted content per leaf. Okay, so I'm going to drop a slider in. It's all going to make more sense once I actually get something in here. Okay, and square leaves. No, it's fine. Okay, so I have these points, right? And what it's attempting to do is it's attempting to essentially put as many of them in a box as possible. Right now my thing is 0, so it's trying to draw a box around each one. And you can see like each one kind of has a volume until it actually runs into another. If I begin to increase that number, now I have 2 points in each one, and it's attempting to create that system. 4 points, 7 points. And so again, these are clusters of like 7, and then where it can't, it's going to subdivide it even further. So it's a way of kind of showing the distribution of those points. If I go back and I adjust this, so you can see this one actually, these kind of have a smaller neighborhood, and these groups of 7 get kind of penned into these boxes. Okay. You can change the settings to make sure that they're always square, and then that's going to change the effect of it as well. So again, if I have the bigger my box, the less subdivisions I get. So it gets more interesting as you have lower divisions, because I can't fully. I have these 2 points here. I have 2 points here. So again, it's trying to go for the minimum amount. The ones that look like they have their own box, they're the ones that are caught between other boxes. So it's just the outline of that. There's actually a gap there. So again, with a quad tree, it's just another way of tiling something. That has a logic to it, though, right? It's attempting to put these things into boxes. Okay, so now you know what a quad tree is. So again, these are all under mesh. Meshing is not something we really talked about, but you could definitely bake a mesh. You can do lots of different things with it. You can convert things to meshes and then apply these things to them. So that's just something that's a whole thing we haven't really talked about. But these are some interesting ways to get some different paneling that we haven't seen before. So I urge you guys to check those out. Okay, last thing I want to talk about is this kind of utility. And there are lots of ways to do this, but I'm going to show you a way. And this is just to kind of give you an idea of how you can use Grasshopper like a utility. So sometimes when you're working on architecture, it's not just about, you know, making like a railing or making a building form. Maybe it's just about making something a little bit easier. Like you have a process that you just want to make a tool for. Okay, you're not just in trying to study something. You have like a repetitive operation that you want to make easier. And one of those things for me was trying to make like a contour model for my class. Like I had this nice kind of model that was already sculpted, but I wanted to send it to laser cutter in nice sheets, you know, and I don't want to have to like, you know, make a bunch of sections in Rhino and then move them and then like flatten them and then arrange them and then label them. It's like a pain in the butt, right? You can do it parametrically, like really, really easily, okay? All using all the stuff that we've talked about in this class. So this is a really good thing that anybody should be able to do at this point. Go ahead and kill this all. Okay, so first things first, geometry. We got geometry. This is a solid model. So I'm going to be taking, what I'm going to do is, I'll explain to you before I do it. I'm going to parametrically take like sections of it. I showed you guys just earlier how I could take a section of a B-rep and a B-rep, right? There are lots of ways to do this. I'm going to make a bunch of planes and use those to cut sections. Then I'm going to take those sections and I'm going to actually orient them to each other, and that's going to create my cut sheets. And then I'm going to put a label right in the center of each of those. And I could put the two things on two different layers when I bake them. So one layer is cut, and that's going to cut the outside, and one layer is score, and that's going to be the label part, right? So I'm going to have the labels parametrically. And then I can adjust the number of contours I take, and it's going to instantly create that like cut sheet for me. Okay? Let's see if it works. All right, so I got my geometry. There is a section tool. If you go into what am I looking at? Surface? No, intersection. Well, it's already there. Intersection. Okay. There is this kind of contour tool, and it works pretty well. But what you have to give it is kind of a start point and like a direction and a distance. So let's go ahead and do that. So what I'm going to do is, okay, so the contour is, the normal is pointing up, so that's fine. I need a start point. Yeah, okay. So we go into number slider, and this is my distance between them, so I'm going to want it to have a big range, pretty much. Okay, so my distance, and I need a start point. So I could do a point. Oh wait. Could put a point on the corner of this thing, and that could be my start point. Okay, so I got my point. Okay, and you can see it's already starting to work. So then I need the number of contours. No, sorry, the normal is fine. No, I don't. This method doesn't do that. So not the number, it's the distance. So if I wanted, 10-foot contours or, whatever. Okay, so that gives me a list of contours. And if I had a topo that was doing something where it was going up and down and I cut through it and I had two pieces of it, those are going to be inside of the group here. So you'll see like N2, N3 or whatever. So you want to watch your data structures so you keep things in those groups. Otherwise, you're going to have these little pieces that are just kind of floating out there and you don't know what group they belong to. All right. In my case, though, this is relatively simple, so it's giving me one line for most of my contours. Okay. Okay. So this is actually what I get. Okay. Then what I'm going to do is, this goes all the way back to week 1. I'm going to use like the orient tool to orient these to sort of like a box that I want to put them into. So I have where these things are, and I want to put them in a certain place. So let's find, so I can get the centroid of each of these. Actually, I don't want to do that, because that's gonna orient them really strange. Let's put orient out to begin with. So again, the geometry is this stuff, and I want a reference plane for that. And I think actually what I'm going to do is, since they're all kind of centered right now, I have it centered in the 0, 0 kind of axis. What I can do that's really easy is I can actually just make a series of planes. So I can make XY planes, because that's what these are. I can make a series of XY planes. I can move them. So I am take an XY plane. I'm going to move it in the Z, and I'm going to move it the same. So if I make a series, so I'm going to move it by this distance. So I have a series. I have 0. Step size is this. And the number of values is going to be list length. It's going to be this guy. And I got to flatten this because, well, no, I can do 10. That's fine. Okay, fine. Be that way. Let's just do this. That is not working. Okay. Plan B. So what I want to do is I want to get a series of these. That's really strange that it doesn't produce. Oh, number of items. I don't want the number of items. I want 11 things. That's weird. Okay. Okay, so plug this back in. Huh. Interesting. So that creates a problem. I want the number of things in the list. Okay. Well, anyway, just do it. For now, I'll just do it. I know that I've got 11. Let's just do 11 items in the series. I'll fix it later. Okay. So we got 11 things. It's not going to be parametric, but so I got. So these are where my contours are being taken from. There's a little data structure thing there. I'll figure it out. Anyway, so these are where those are being drawn from. So if I plug this in, it's going to give me a plane where each one of these is. And actually, I'll probably just kill that last one. So it's actually, yeah. Okay. So I've got my contours, and then I take where those are in terms of the planes. And I didn't take them by the area because I want each of these to be arranged in the same kind of in the same kind of volume. Okay. So there's a series of planes. Okay, and these are where they're going to be taken from. So we've got these. Okay. This is going to hurt me later. I'm going to have to fix this data structure. Okay, and then what I'm going to do is I'm going to create a series of containers for these. So I'm going to go in and I can just I'm going to make a rectangle that's the bounds of this thing. Okay. And there's other ways to do this, but okay. So that is my kind of tray. Like that's the biggest size contour I'm going to have, right? That's the biggest piece I'm going to have. And so what I can do is I can take that curve and I can reference it. Okay, now I can hide it. So these are where I'm going to move. I'm going to reorient all these pieces into this shape container. Okay, and then I'm going to move them in the x-axis. Unit x. Series. Okay, so I've got a group of these, and I can do this like mathematically, but for time I'm just going to eyeball it. So I'm just going to make a hellaciously big slider. Okay, so, and again, what I've done is I've got a series of these things, and they all need to match up basically. So whatever, again, this is kind of hacky, but I'm going to make a number slider for the number of contours, and I think I had 10. So these need to match up. So the number of planes I have has to match the number of containers I have. Okay, so these are where I'm going to put these. Not going to work here. Okay. Let's see here. Yeah. Okay, this is not perfect, but you get the idea across. So what this does is essentially, I've used that to distribute Okay, let's take a look at this in 3D. So using the orient tool, I can take these contours, and then I made a container for them, and then I just reoriented it from the contour to the container, and that gives me the sheet of cut lines for these. Okay, and then I could go through, and I could change the contours, and again I have to. Well, 0 is not gonna work. I can find out what that is, get the length of it, and then as long as I have the same number here for my containers, I have the number of my contours. Okay. So the last kind of piece of this that I want to show you is like how to label them, and I'll put up a fixed definition of this online later. The last thing I want to do is put a label on them, and so one kind of easy way to do it. There's better ways to do it, but an easy way just to keep track of them for yourself, so that when you kind of trim them, you know what's what. Is you could use an area component. So this is going to give you the center of your piece, okay? And then I could go into my vector stuff and get a text tag. And I could take that, and that's going to be the location of it. And then the text of it is just going to be, if I just make a series of numbers, and actually I'm going to do an integer so that they're rounded. So I have a series of numbers from 0 to whatever my maximum number is. And then I pipe it in for the tag, and I'll hide this. So then they're all going to be labeled. They're going to be numbered. Okay, and so again, you bake those to a separate layer. That's your score layer, and then you bake the outlines to your cut layer. You know, if you get all this like working, you have kind of a tool, and you can save this for yourself. And then anytime you needed to make a contour model for yourself, right, you just run the script on that piece of 3D geometry. Okay, so this isn't, you know, there's lots of ways to make this more efficient. You could make the numbering a little bit different, like maybe have the number be like in the corner of it. You could take that corner piece and then offset it, but I like it in the center. So anyway, just a really basic way to take you all the way back to the beginning to look at how we can use like the orient tool to make this process a lot faster for ourselves. Okay, depending on how many contours you have, you know, this stuff can take like forever to cut out, and or to move in your digital model, and this really simplifies the process. Okay, so anyway, I hope this is kind of useful stuff for you guys. If you guys have questions, you know, if you want to use this for studio work later, I'm always around. I hope, you know, you guys this isn't the last time you use Grasshopper or any of this stuff. So for Thursday, bring in any questions you have. I'd like to check on your progress, and hopefully we'll get everybody through for Project 3. Thanks.